Take a look at this next lesson. This lesson's on circular motion now. It's on circular motion and Newton's law of gravity. And if we think about this, if we look at this example here, let's start with a simple example. Start with a really simple example. So, if we spin anything in circular motion, right, we recognize right away that if I wasn't continuously spinning and the rope wasn't attached and I just cut the rope, what would happen to this object? Yeah, it would fly off. Which way?
Wherever you cut the ropes, like if it's on that side, it would go that way.
Yeah, good answer. The idea of that, you think about softball. When you're a softball pitcher, it depends on where you release the ball, doesn't it? If you release the ball, so imagine I'm a softball pitcher and I go like this, and I release right here. Where's it going to go? Straight down to the ground. It wouldn't make sense, right? If I'm a baseball player, I would throw and I would release usually at the top. For baseball, you do come down the ball a lot more. Softball's a better example because softball, when a softball pitcher pitches, they release where? Where? At the very bottom. And when they release at the bottom, what happens? The ball moves parallel to the ground. So the circle looks like this, and the ball moves like this. What's the word for that from the other day we used? What's the word for that? Draw yourself that diagram real quick. Draw a circle. Okay. Draw the softball at the bottom of the circle. And then draw the direction that the softball would move if released at the bottom of the circle. It's a terrible circle. So, the person's arm would come around like this, right? Well, let me do it this way. I drew it this way. Ready? Here's the ball. Softball pitcher starts. I'm not a softball player, but I don't know if I can do this arc right, but I think they take a step. A step. And you come over. Is it a window, right? When you come around, do all softball pitchers go to the window?
Yes. Well, if you're high school, yeah.
Yeah, okay. So the arm starts up here at least. Maybe they come around and they release down here. And then the ball moves that way. What is the word that represents this kind of a figure?
Momentum.
No. Good try though. You said momentum. Yeah, substitution, okay. What's the word that represents that? Come on, geometry. Was it? Where are we rolling over here? He had his hand up. You got like a tangent. So we're going to talk. Remember tangent? He touches the circle once. You need to know that vocab. Secant was when he cut the circle twice. Like a chord, right? A chord goes through the circle twice, but it stops. It's a segment. Anyway, so listen. So in this section, we are going to talk about what's called tangential velocity. It will be on the next slide. You don't have to write it down yet. Okay, and the tangential velocity is the velocity of the object if it were just released at that instant. So if I was spinning, there was a good answer, by the way, I'm going to tell you earlier, because when I was spinning the rubber stopper, I always ask, which way is it going to move if I cut it? And people say, they'll point in one direction. I'll say, well, it depends on where it is. And that was what you said. It really does. It depends on when you cut it. Where is the stopper? If I'm spinning it like this, and the stopper's over here, it's going to shoot that way. If I'm spinning it like this, and the stopper is over here, it's going to shoot that way. So think about like a cowboy with a lasso. When they would do this with a lasso and they would throw it forward, when are they probably releasing? They're probably releasing when it's on the side because it has that forward motion to it because the circle was like that, right? So you have to consider the fact that when it's rotating and released, it moves tangent to the circle. That's the first big part of today. Second part is going to go, this lesson is going to be gravity and the interaction with gravity. How many of you have seen Family Guy before? I think I gave this example earlier in the year. Did I talk about this? You know it? Okay. Yeah.
I actually watched that episode.
So there's an episode where Peter, I don't know the reason and it doesn't really matter, but in this episode Peter starts gaining more and more weight. Peter's, if you don't know Family Guy, is the main character. He's like a heavy guy in general, but he's gaining more weight in the episode. And Brian is his talking dog. And Brian's standing next to him and he's like, Peter, what are you doing to yourself? Look, you're out of control. Come on. You got to keep your head up, whatever he's saying. I don't even know what he's saying. But at the end he starts talking and he goes, look, Peter, you're even developing your own gravitational field. And he takes the TV and he throws the TV at him, and the TV starts orbiting around Peter. And then he takes a chair, throws it at him. And what happens? What's the reason for that? Is that if you think about like the Earth, the mass of the Earth is such a great value that things are able to rotate around. That's how satellites rotate. That's how the moon rotates. So the idea of mass, anything with mass creates a gravitational field. So if you are in the middle of space, you are creating gravity around you actually. But the gravitational field that we are in, which is the Earth's, is so much bigger than what we can create that it's insignificant. But really, like this eraser and me, we're pulling each other toward each other with gravity right now. Everything is pulling toward each other. The desk pulls toward the podium, the camera pulls toward the computer. Even things at infinite distances have gravity. Gravitational pull can never go away. It just becomes so small that the force is like 0.000 with like a million zeros before it gets to number 1. So if the force is so small, F equals ma tells us that A is pretty much nothing. So you don't feel acceleration or pull because of the iPad, yet it is pulling you. It's kind of interesting to think about. Anything that's in space that has mass warps the space around it, and when you warp space, when you change the shape of space, you actually are pulling things towards you. It's a good example of gravitational waves I can show you.
So if like the Earth's gravity was like a lot smaller, could you technically like pull something to you?
Yeah, but it wouldn't be feasible. You couldn't exist on a planet that wouldn't have enough gravitational pull to keep you there because it wouldn't hold the atmosphere. It wouldn't hold anything. You know what I mean? So theoretically speaking, sure. Realistically, no. It wouldn't exist. So those are the two main concepts we're going to go over. Okay, circular motion with tangential velocity, and that's what we're starting with, and gravitational force. So we already mentioned this, tangential speed, I'm going to use the word. Speed is the speed of an object when it moves in circular motion that's tangent to the path. That's tangent to the path. Now, here's a little follow-up question for you. So draw yourself another circle. Actually, I'm going to use a little shape generator. Okay, so this object is, let's say, right here on the circle. Here's the center of the circle. Oh, that's a bad color for this. So this object is on the outside of the circle. Now, at this point, let's say it's moving in a counterclockwise direction. Therefore, the velocity would look like this right now. That's the vector we were talking about a minute ago. So it's a softball player, right? Release at the bottom. It's going to go in that direction. So right now it's moving, again, counterclockwise. If I were to, and I asked you this earlier, if I were to release the softball a little bit early right here, we saw that it would spike into the ground. So that's the direction it would go from there. So if the softball player accidentally released back here, the ball would shoot right into the ground. If they release at the right time, it moves horizontal to the ground, or horizontal. So what's happening to the direction of this vector? It's changing. We can see that the vector is angled down to the right, and then it's angled only to the right. So as a result, if we think about this, we call this tangential speed for a reason here. Because actually, tangential velocity is constantly changing. Velocity, if you remember, is a vector. When something is a vector, it has two things that make it up. What are those two things that make up a vector? Two things. This is where you really just got to memorize at this point for some of these things, right? There are two things that make up a vector, always. Two things.
X and Y.
Close. Not X and Y. Direction is one, so X and Y works for one of the things. So direction. And the second part of a vector? Magnitude. Magnitude means the physical number. Direction means like northeast, southeast, southwest. Which way is it going, right? So what we're seeing here is this. Although the speed could be constant, let's say that at these locations, let's say that the speed here is 5 meters per second in both cases. Okay, the speed is 5 meters per second in both of these scenarios. The velocity's magnitude is 5 meters per second. That's not changing. It's still 5 meters per second. But the velocity direction is what's changing. The velocity was angled down to the right, and now it's only angled to the right. So therefore, believe it or not, there's a change in velocity. It's not the number. Okay, it's not the number. It's not the value. The value is 5. The value, the magnitude of the velocity is going to be 5 the entire problem. But the direction is constantly changing. If the direction changes, the velocity technically changes, even though the number's not changing. Now, keep up with me for a second. If velocity changes, what do you have? There's one word for this. if velocity changes.
Acceleration.
That's the definition of acceleration. A change in velocity over time. It's not the number. So again, it's not like the acceleration is like, okay, I have a starting velocity of 5, ending velocity of 12, there's an acceleration clearly. It's not obvious here because the number hasn't changed. You're at 5 meters per second, and you still are. But the direction you're traveling is changing, so technically the velocity is changing. When velocity changes, you create acceleration. Now, the acceleration in this problem is a little bit different. It's not like your normal acceleration. It's not like you're only moving in one direction. So let's say, think back to kinematics from chapter 2 and 3. Ready? I'm walking across the room. Slow, faster, faster, faster. Which way is my acceleration directed? Point. Which way is the acceleration directed? Yeah, it's got to be the right because I'm speeding up to the right. If I was slowing down, which way does the acceleration act? Yeah, back against me. How are you going to draw the acceleration here though, right? How do you know what happens? Well, let's actually use a conceptual derivation. I could show you some vector analysis, but it gets really complicated. I can actually just make it explain a little bit easier. Imagine back to the example with the rubber stopper, our last one. So you're spinning a rope around, okay? Physically speaking, what is keeping that rubber stopper from launching toward you? Physically. The string. Very good. Good answer. Because most people say you're spinning, so you're keeping it moving, right? My spinning is actually making it want to move away. The spinning, the speed I'm giving it, is making it want to move tangent, to move away from me. The rope or the string is keeping it. What force acts in a rope from earlier this year? What's the force that acts in a rope? What is it called? Pull a rope, it has what in it? Come on, guitar players, what is it? Tension. It's got tension in it, right? You pull on a rope, it's got tension. You let a rope go, it has no tension. So in this case, the tension in the rope is what's keeping it moving. It's what's keeping it moving in a circle. So here is what we have. When it's at this location, the tension in the rope pulls it toward the center. When it's at this location, where's the rope? Well, the rope is now here, also pulling it toward the center. No matter where I am along the circular path, the rope pulls me back toward the center. If it didn't, I would move away from the center. Think about it logically. You need something to keep you moving about some center point. That's physically what you're doing when you spin a rope or a lasso. You're keeping it moving about a center point, so it always gets pulled back to the center. That's the tension pulling it back. Whenever you have an overall force in some direction, you also have to have acceleration. What law tells me that? That when I have a force, I have to have acceleration. What law? Yeah, Newton's. F equals ma, exactly. If you have F, you have A. It's the way it is. If you don't have F, if the sum of the forces is 0 somehow, they're balanced, you don't have A. We've talked about that several times. So as a result, because there's a force toward the center, there's also acceleration toward the center. And we call that AC. The acceleration and the force always act in the same direction. So in these problems, when we see circular motion, the acceleration is going to be toward the center always. It's kind of weird, but it's the reason this is kind of easier than the other one, that's it. It can only be toward the center. Whenever something's spinning in circular motion, the acceleration is always toward the center. It's not going to be positive, negative. It's not going to be left, right, up, down. It's always toward the center. Okay? Now, you're probably wondering, why the hell do I care about all this? Oh my God, going with circular motion. So much stuff in everyday life behaves based on these laws of circular motion. Anything that is rotational behaves on these laws. Anything. A wheel, a CD player, the hard drive of older, not new computers that have solid states, but old hard drives that have spinning drives. They have a certain amount of RPMs that they rotate at. So all of these things behave with rotational motion. So we have to consider the fact that this acceleration is only toward the center because the force is toward the center. If you look at these vectors, you can do what's called a vector analysis or a vector sum and see that it's also acting toward the center. Okay, but it just gets a little bit annoying and clunky to do it that way. So I like to think about physically how it's working.
So like, if a car is accelerating too fast, is that why like the wheels might be blown out or something?
Yeah, they usually slide out, but yeah, they don't. I mean, they could blow out also. Oh, you mean? Blowout is it's actually like a failure point in the tire where the pressure exceeds the allowable pressure in the tire frame. it's not really about this. I mean, the speed definitely affects it for sure. But I would think about this more of like a car around a track. If a car goes around a track, if it's going too fast, what will happen? It'll slide out. That's this example. How many of you have seen NASCAR before? Not necessarily a race live, but ever even see it on TV where on a commercial? Have you ever seen cars go around turns in NASCAR? Can you explain what it looks like?
Don't they drag?
Don't they what?
Drag.
What do you mean by drag?
Like they turn really fast and they hit the brakes and they just
They slide a lot, they drift. They drift a lot for sure, but I mean physically. Do you know, Caroline, around the turn, the street, you see what happens to the street around the turn? The paveway, the roadway. So normally they're traveling like this.
It goes like a little higher.
Yeah, you notice it like kind of goes up a little bit. It's called a banked turn. If you've all done it, whether you realize it or not. You enter an entrance ramp to a highway, they're usually banked. When you take an exit ramp that says 30 miles an hour on the ramp and it shows a truck tipping over, usually those road turns are banked. And it prevents people from toppling outward away from the circle or moving tangent off the circle. Imagine this is the car and it starts to slip. Well, here's the actual entrance ramp. The car's going to slide off the side of the road like that. So what is keeping the car from sliding away from the circle? Physically, what's keeping it? No, come on, think about the last example with the road. What was keeping it? Friction. What force is really the answer? The answer to all these questions really is what is the force that's doing it? In a minute, we're going to see an example where we're going to go through a bunch of these that show all the different forces keeping it in circular motion. But I need you to recognize that in this case, something is keeping it from slipping away. It's the friction pulling it back to the center. So here, see how it was Ft? If this were a car, this would be Ff, the force of friction. The friction in the tires is pulling it back. Why is the turn banked? It's an inclined plane. Ready? Follow my hand. So what's his name? Jeff Gordon? Is that right, Jeff Gordon? Is he still a racer? He retired? Oh, yeah, he's like the only one I know too. So Jimmy Johnson. He's the coach of the. Why am I thinking Jimmy? Isn't he a football player?
Coach of the Dallas Cowboys.
Yeah. Is he also a driver?
There's a different person.
Oh, yeah, it's probably many Jimmy Johnsons, true. All right, so anyway, Jimmy Johnson's driving down the road, and he goes to take this bank turn. And as he turns, right, the turn looks like that. So if you were to literally look at the road and slice the road would be banked like this, and it would be flat at the base. Think about the earth is this way, but the turn is angled up because the car is on an angle, right? So this is just an inclined plane. And inclined planes naturally allow you to move down the plane. Remember the first quarter project, literally the object gets pulled by gravity in only the direction down the plane. They didn't do a lot of math on inclined planes, but that's the reason the turns are banked, because not only does friction help you stay to the center, but the gravity of the car pulling down the plane also keeps you toward the center. So you have two forces helping you really with a car going around a bank turn. It's gravity down the plane, and it's friction between the tires and the road itself. So let's look at a quick example. Imagine you're on a merry-go-round, and the merry-go-round has 3 horses at 3 different distances from the center. So horse 1 is a distance away of R, horse 2 is a distance away of 2R, horse 3 a distance away of 3R. And the floor of the merry-go-round moves together as like one body. Okay, it's not like there's 3 tracks and each track is moving at a different speed. The whole body of the floor rotates like this. Okay? But the outer horse is out here, inner and middle. So you got 3 horses going like this, together around the track. Is that clear, the figure? Can you visualize? All right, question says, which of them has the highest tangential speed? Speed. I don't care about the velocity right now because we know the velocity changes because the direction is changing. But which has the highest speed? What is speed defined as? Velocity is displacement over time, right? We know that from earlier this year. What's speed again? Who remembers speed? Good. Distance over time. Which horse travels the furthest distance? I'm not good at drawing circles. That's kind of. Which horse travels the furthest distance? Which one? Yeah, the one that's furthest away. I mean, just literally look at the 3 lines you see. Those are 3 circumferences. Those are 3 circles that are concentric. Remember that word? Geometry? Concentric with the same center. Your Latin or your Greek, con, means with. with the same center, concentric. So these are 3 concentric circles, and all of these circles here, all of these circles have these horses moving tangentially at 3 different radii. If there are 3 different radii, what are also different? The distances traveled, because those are just circumferences, really. So the outer horse has the highest distance traveled. What about the time? Which horse takes the fastest? Which is the slowest? Well?
Which one goes the fastest in a circle?
Yeah, which horse takes the least amount of time? Which takes the most amount of time?
The one in the first one takes the least amount of time to go around the circle.
First one?
Yeah.
I mean, if they were moving separately, I agree. Ryan?
All of them.
They're all moving together right now. But if they were moving separately, you're right. The inner horse would go, right? They're connected, right? So be careful. So they're taking the same time. They're not taking separate times. They're literally doing this, right? Okay, they're moving almost like synchronous, in tandem. I don't know. Is it synchronized? I guess we use the word. Yeah. So all 3 of them moving together. So time is the same. So if the time is the same for all of them, but the outer one travels a lot further, the outer one is moving the fastest. So this one, S3 would be greater than S2, which is greater than S1. Okay? No, it's not. The tangential speed of object 3 is greater than 2, which is greater than 1. Agreed. But you could say that the angular speeds, I'm not going to really test you on this, but I want you to just know this. The angular speeds are the same. How much angle do they complete in one revolution? How many degrees is that? And doesn't it take them all the same time to complete 360, we said? So the angular speed is 360 degrees over 5 seconds. Or whatever, 6 seconds. 60 degrees per second. So they have the same angular speed because they're moving together. But the outer one covers more distance. How many of you have run track, cross country at some point in life? How does it work in a race, like a mile race? Does everybody start at the same point?
No.
They never start at the same point. Why?
That's unfair.
It's not fair, right? If I get the inner lane, I got to run a shorter distance than you on the outer lane, don't I? Same thing here. Okay, this is taking a lot further of a distance travel than the other one is. Apologize. North Carolina, every day. Like in North Carolina, Florida, somebody gave my number out. A student that hated it, I think, really. Somehow got him. Seriously, for the last year now, I get solicitation every day. I apologize, sorry. So the speeds of these are different because they're covering different distances here. So in a race, the person on the outer track has to travel a lot further, so it's a staggered start. In a mile race, you see somebody starts here and somebody starts here, and then they go around the track like this. This way. No, this way, sorry. They go around the track like this because the inner person can easily catch the outer person. But in the end, they still run the same distance, right? They still run the same distance. We have a minute. Let's quickly go over this, talk about this theory behind this last word. No, we've done this. 10:03. Let's talk about objects in circular motion. We already quickly went over the idea of the force acting toward the center and the acceleration acting toward the center. So let's actually jump right into the actual equation. So we're going to talk about something called AC, and a minute ago I drew that on your diagram. It stood for what's called centripetal acceleration. Okay? We want to say circular because it's moving in a circle and it's AC, so it's tending to say circular acceleration. Centripetal, though, happens to mean center seeking. That's why we use that word. If you think back to the diagram from a little while ago, we talked about how an object moving in circular motion, when it's moving in this direction, the acceleration at these locations is always toward the center. It always pulls it back toward the center. The rope pulls it back toward the center. What keeps the moon going around the earth? Gravity. So instead of the tension in the rope, right? Instead of the tension in the rope keeping something moving in circular motion, gravity keeps the moon moving around the earth in circular motion. So depending on what's happening, it provides a different thing. Now, let's jump right into our formula here. So our formula describes the centripetal acceleration as two things. The tangential velocity squared, that's the numerator. You want to write that down, tangential velocity squared, over the radius of the circle. Over the radius of the circle. Have you heard the term centrifugal before? How many of you have ever worked in like some sort of a medical institution? Interning or anything like that? One person? All right. Do you know what the word centrifuge means? From biology, did you learn about centrifuges? Separates blood into different densities, plasma, the different parts of the blood. Each part of the blood is a different density, so it spins blood, and based on the density of the blood, it sorts it by the different types. And then the furthest one out has the like most or least dense, so it uses the different densities to sort blood into different pieces or separate it. So something that spins quickly. How many of you have been to a carnival and you get on the gravitron? You know what the gravitron is? It's the one that spins really fast and you're like tied to the wall. Don't you get sucked to the wall and you're like floating? Isn't it really cool? That's the centrifugal effect. See that? Center fleeing, that's centrifugal effect. Different from centripetal acceleration. Okay? Centrifugal is center fleeing. Centripetal, center seeking. So centripetal is the acceleration that's keeping you from not moving away because of centrifugal. Centrifugal is the idea that you want to move away. Centripetal is keeping you moving toward the center. Okay, we'll go over the dimensions of this tomorrow. But R is the radius of the circle here, not the lever arm from torque, different arm. Horses too. So let's start this one. A car moves around a track. It moves at a constant speed. Notice I said speed because if it's turning, remember the velocity changes. The minute your direction changes, your velocity changes. Even if the magnitude of it is still, say, in this case, it doesn't actually tell you. We're trying to figure out. But even if the magnitude is like 5 meters per second, the direction changes. Yeah, it's 5 meters gross. I'm going to retie that word with something else. So if the radius of the track is given as 20 meters, and the actual acceleration that the car feels, or the person in the car feels, is 6 meters per second squared, then what is the speed of the car? Now, if the car goes faster and faster and faster and faster, it's going to feel more and more and more acceleration. Where have you seen this before? Where do they use something that goes really fast in some sort of a circular motion to simulate a lot of acceleration? One of you's got to know.
Like NASA?
Yeah, there it is. Very good. Do you know, did you see it in a movie or did you just read about it at some point? Because I've also seen this in a movie before. Anybody know what movie it's in? It's a really corny movie. Have you seen Armageddon before? Have you heard of Armageddon? It's an older movie, so you might not have seen it. It's like an old movie.
Bruce Willis, right?
Yeah. Bruce Willis and like Aerosmith was the big artist, the singer in the movie. But it's a decent movie. But at one point in the movie, they're training these oil miners to go up to a comet to then drill into the comet, deposit a nuclear bomb, explode the comet so that it doesn't hit the Earth.
Oh,
It's like this, this Armageddon. The Earth's about to die, but these guys are the last savior of the Earth. They're oil miners. So they have to train to become astronauts in like 2 weeks, which is absurd. But they got them in these things, and they have them in the end, and they spin at ridiculous speeds. Why? Because as you spin faster, what was our formula? Our formula here for centripetal acceleration is Vt squared over r. So if I increase the tangential speed or velocity here, I'm going to keep increasing this at a squared rate, right? So if I double this, this goes up by 4. If I triple this, this goes up by 9. If I quintuple 5, this goes up by 25. So as a result, if they just spin something really fast, it makes the astronauts, or trainees, whatever they are, feel like the acceleration of gravity is what they would experience when leaving the Earth. So, what's Earth's gravitational pull? So if you got an answer, in this case it's less than Earth's pull, so it's almost like you're in a free fall. If you got an answer of like 27 for acceleration, that means that you're feeling what are called 3 Gs. Ever hear that phrase before? If you're on a roller coaster and it said, this roller coaster exhibits 5 Gs, it means you're feeling 5 times gravity. At a certain point though, the human body can't withstand that and people actually pass out. Here's the reason why. You want to know?
At what point is it?
You want to know why? Oh. Okay. Okay. Maybe they can help. Yeah.
Is it because the blood rushes to your head?
The other way usually. It rushes away from your head.
Oh.
It could be either actually, right? But usually, think about it. If you're looping, your blood wants to flee, right? Center fleeing. Let's go to the cup again. The water in the cup, when it's at the top, which way does the water want to go? It wants to go out, right? It wants to actually fly away. Gravity's pulling it down, normal force is pulling it down. But as I spin this, the water literally wants to get launched up into the air. But it's getting pushed back down by the normal force. So when you're inverted in like a loop-the-loop, your blood rushes to your feet at the top, away from your head. Your head is in the middle. Here's your head at the bottom. Here's your feet at the top. Your blood rushes to your feet. If it rushes, if too much of it rushes or too quickly or for too long of a time period, you'll black out. And that's what happens when you go under like 4 or 5 G's of Earth's gravitational pull.
Can someone survive like 6 or 7 G's?
The human body is very interesting. So it's not like there's no number that's the final answer. There are probably limitations, and they're probably like record set, I'm sure, of people that have undergone ridiculous amounts of acceleration of gravity. But it's not like there's like 4 G's and you're dead. You know what I mean? It doesn't work that way. It's not like a blood alcohol content where there's like a threshold, right? It's not the same as that. But I just want to give you guys a little synopsis so you understand where this could really be used. And NASCAR drivers, when they go around those turns, do feel several multiples of Earth's gravitational pull because it goes so fast at such a low radius too. Because if I decrease the radius, remember, how are these related? How are these related? What's the word for that? Indirectly. So if I decrease the radius, what am I doing to the acceleration? Increasing it. Remember, these are always indirectly related in formulas. If this goes down, this goes up. So NASCAR has small turning radius and high velocity. So lots of acceleration. Anyhow, that's a little synopsis because this is really a boring problem. We're just plugging in. We're trying to figure out the speed of the car, VT, so I can plug in numbers or solve algebraically. I'll plug in numbers just to be simple for today. If I want to get rid of the 20, I see that 20 is in the denominator. I multiply both sides by 20. And then as a result, I take the square root of 120. It's going to be close to 11 because root 121 is 11. .95. Okay, so the concept here, again, very simple problem. I want to give you a little application of it though, because this could be ridiculous just to plug each other. All you got to do is plug in your acceleration, plug in your radius, solve for VT squared, square root. Okay, so that would be the velocity necessary with a radius of 20 meters. Now, in Armageddon, just to give you a little fun fact, I would estimate that the radius of the object that they were using to spin them was probably about 15 meters. Because if you think about the size, like in the movie, think about like a person, right? A person's width is not even a full meter. Your width, your length of your body is about 2 meters, and they could have probably fit maybe like 15 or 20 people in that space, and thinking about the visual, what it looked like. So the radius in that movie would have been probably a little bit less, maybe around the same, you could say. But this is only not even Earth's gravitational pull. So look at this speed right here. You would need a lot higher speed to get something like 3 G's, because 6 would become 27. And then you do 27 times 20. Right, 3 G's would be around 27 or 30-ish, actually close to 30. 9.8 times 3, 29.4 or something like that. Yeah, 29.4. So this would be 29.4 times 20. And then you'd square root that number. You need a lot more velocity, is what I'm saying, to feel some sort of a significance of 3 G's. I don't know what it is, but I'm curious. That ride, the gravitron, I wonder how many G's that actually exerts. It depends on the velocity. You don't know. You have to figure out the angular velocity, convert it to what's called the tangential velocity, and then see how many it is.
I'm saying, what is it exactly?
Oh, sorry. It's the one at like an amusement park where it's like that, and you're on the inside, and you're like taped to the wall. You're strapped in. There's straps to hold you into the wall.
You're not even strapped.
Are you even strapped? I think now they put safety straps now.
Oh, yeah.
I think they do now because of laws. You can strap. But it used to be like you stood there, and you could invert your body and go upside down in the middle of the ride.
Unstrap yourself.
Oh, obviously.
Yeah, that's.
But I mean, like to have safety straps. People used to like, you come off the ride, and they'd be upside down. And you're like, what the heck? And you could literally like crawl, edge yourself around. Because you're getting sucked to the wall the whole time. It's like the water getting sucked to the top or the bottom of the cup when it's at the top.
Yeah, the gravitron is 3 G's.
Say again?
It's
3 G's?
Yeah.
All right, there we go. So the gravitron is 3 G's. Do you know can you pull up the dimensions of it?
Yeah,
If you can get the diameter or the radius of it, we could figure out what the actual velocity is necessary to get up to 3 G's.
Is that why a rocket has to accelerate more than Earth's gravity in order to achieve that?
There's so much
Yeah.
You need more than 9.81, or else what happens if you're 9.81? You're pretty much not moving. It's a hovercraft. Think about a hovercraft, guys. How does a hovercraft work? A hovercraft has to balance your weight to hover above the ground. So what acceleration does it push up with? 9.81. So as a result, you're in a state of equilibrium, you're balanced, you're hovering off the ground. But to get off the earth, you got to accelerate with more than 9.81.
It's 56 long by 47.
56, it's not a circle? It's not a circle?
No, I'm just reading.
Yeah, that's odd, right? You think they'd give you a diameter or a radius, not a dimensional.
Not all of our circles. I've been on this like outdoor.
Really?
Yeah. Oh yeah.
Yeah, with the width being that.
But you would give height, you wouldn't give length. If they give you width and length, it assumes that it's an elliptical shape, right? Because if you got a width and then the length, it stretches it. If they give you a height, either way, whatever it is, that's how you would figure out and determine the value necessary, right?
Oh, it's 13, 46 inches high.
That's the height. Okay, so 40 by 30. So we'll say about 35, which is average. So that feet, you convert it down, it's like 12 meters or so. Actually, somebody asked, was it this class that asked about this earlier in the year? Somebody asked about like an amusement park. They do have a physics day. You can figure out when that is. I mean, I don't know. I've never done it before. Google it for us. Just take a look. I don't know where the nearest one is, but I would do it on like a physics day if we were allowed to, for sure. But we wouldn't just go to an amusement park to go. I don't actually go on rides. Not other than lame.
Would you let us go on rides?
Obviously. No, you can't go on rides or go to the park. I don't know, I never did. I get really sick. I have bad motion problems. Airplanes and stuff, I feel really sick. Any sort of acceleration. I wanted to be an astronaut when I was a kid. And then I went to an amusement park and got on like a Ferris wheel and threw up. That was the end of those days, you know? True story though, I'm not kidding. I'm terrible. He's asking about like a field trip or something like that as a class. They have a physics day. That's what he's looking up, right? April 21st. We do a little research, I'd be happy to go. It depends on what the day is, what's going on at school, if people can leave, you know what I mean? It's not a one person.
Now so they plan around us.
Well, keep in mind that the year calendar is made in the summer. So as soon as there's something on the calendar, I can. On a Friday? All right, email me the link to the info, please, and I'll further investigate.
Looks like you have
That'd be so cool.
Yeah, I would definitely be down. We'd have to get obviously like a bus and stuff like that, but that would be fun. It would be a fun day.
And there's a form
Yeah, and you'd have to do groups.
And there's like a
I would just call them and do it all over the phone. I'm not going to do all that. But just send me the link to the info, please.
Wait, the 28th.
What was the date? 21st. I hope we're not on vacation then, right?
No, we're not.
Actually, that'd be even easier if we
It's
were.
the Loyola Players Spring.
Is it really? On that day?
On the 21st.
that's true.
All right, let me look into it. Yeah. All right, let's continue. It's good to talk about this, but let's focus. Now, we talked about centripetal acceleration. Where there is acceleration, there must also be force. Okay, deceleration. Force. There must also be force. Okay, because remember, F equals ma, Newton's law. If you have acceleration, you have to have net force. And earlier, we spoke about why was there acceleration? The reasoning we gave was because there was force. So it's like a catch-22, right? Why was this object able to stay in circular motion like this? Because the tension in the rope is keeping it in circular motion. Tension is a force. Because there was a force, we said there was acceleration. Now I'm going back to the converse of that. Because there's acceleration, there must be a force. So we go ahead and look at this force. And we think to ourselves, Newton's law says F equals ma. But what is A? What is the formula for A that we just wrote on the previous slide? What's the formula for A? Just read it to me. Jake, what do you got? Yeah. So replace A right here with A like centripetal because it's circular, which is really VT squared over R. So F equals ma simply becomes that for circular motion. So write this down as a little asterisk. F equals ma still works for horizontal and vertical motion, but for circular motion, This is your formula now. Instead of using F equals ma, I mean, you could use F equals ma, that's fine. Right? You could just do this. You could use F equals ma still. So you could use this formula, but you might not know the acceleration. Maybe you know the velocity and the radius, so this is what you're going to use now. And remember that Fc is not a real thing. Fc is whatever force is being provided. So when I just spun this, what would I put instead of Fc? What would I put? What force is it? What force is it that's keeping this in motion again? What is it called? It's the one word? No, it's the word that we really didn't talk much about. No, it's in a rope. In a rope. Tension. So in this case, I would call this instead of Fc, Ft for tension. If it was the Earth going around the sun, what keeps the Earth going around the sun? Fg. That would go right here. If it were the roller coaster example, at the top of the loop-the-loop, you got, ready? So take a look, please. It's going around the top. It's on the roller coaster. It's on the track. It wants to go away, but the normal force pushes back, and so does gravity. So this would be Fg plus Fn. Okay? So whatever force is directed to the center in all of these problems, when something is going in circular motion, whatever is keeping it in circular motion, in this case, for a roller coaster, Fn and Fg both pull to the center, those go in place of Fc. And then it just becomes this formula. So just like F equals ma with forces, we just pretty much list all the forces acting on the object. In this problem, I want you to recognize you list all the forces acting in or out of the circle. Remember, for x direction, to the right was what? Positive or negative?
Positive.
To the left?
Negative.
Simple, right? Here, in is positive, out is negative. Write yourself a little note. If a force pulls inward, it's a positive value. If a force pushes outward from the circle, it's a negative value. Okay? Into the circle, radially inward is considered positive. Radially outward is considered negative. At the bottom of the loop-the-loop, what does the formula become? So the car already went through the loop-the-loop, and now it's at the bottom again. Matei?
Fg minus Fn?
Close?
Fn minus Fg?
Yeah. Fn acts in, and Fg acts down now. Again, take a look at this object at the bottom, please. After it completes the loop, gravity is still pulling down, but now Fn pushes back up because it wants to move out. Remember, it always wants to move out of the circle. Fn is pushing back. So this equation would become this. Fn minus Fg equals mv squared over r. Please remember, write this down as a little note to yourself. Into the circle is positive force. Out of the circle is negative force. Okay, it's not about being up and down here. Please don't memorize up and down. It happens to work coincidentally. But anything out of the circle is negative. Anything pushing in is positive. Okay, it's not because it's up and down. It's because it's in the circle or into the center versus out of the center. With that said, let's take a look at an example, please. Oh, sorry, before we do that, let's talk about certain types of forces. I thought I had that example right after. We'll do that example next. So we mentioned a couple of these already. Let's take a quick visit and look at these other examples. The first one, what's the answer you just gave me a minute ago? Jonna, what was the answer to this one? You said it? Tension. This one is tension because we know when we swing something on a rope, the rope literally provides tension. This is what I'm doing as a tether ball. And then it goes back. Ever seen a tether ball, the game? Yeah. Napoleon Dynamite? Okay. A car traveling around a circular track. What did we talk about yesterday? What kept it in motion?
Centripetal force.
What provides? Remember, centripetal force is not a real thing. What is it? Friction. The tires between the road keep the car from sliding out. Now, remember, I also talked about if the turns are banked, if you have banked turns, gravity also pulls you down the inclined plane. So it's really friction, but it could also be gravity helping you if it's on a turn that's banked. because gravity pulls you down. It keeps you in circular motion. Roller coaster, we just mentioned, a loop-the-loop is normal force and gravity. Or, we don't know about gravity every time, it changes. Remember, if it's at the top, gravity helps. It pulls you back to the center. When the loop-the-loop is at the bottom, gravity pulls down. How about a stunt devil airplane? You ever see those? They're called like the Blue Angels, I think. Yeah. They fly over Jones Beach. Is that the name of them? Yeah. What keeps them in circular motion when they do a loop-the-loop or a barrel roll? What forces act on airplanes? What are they called? Anyone know what the names of those forces are? What allows an airplane to take off? What's that force called? Lift, hence lift off. And we have lift off. Lift force is what gives the plane a little bit of a buoyant feeling. What keeps the plane from being able to fly as easy as it can and flying, get up in the air without any velocity? What keeps you from doing that? Gravity. What else? Yeah, gravity's right. Yeah, gravity. Yeah, but what do you call that in the air when it's friction, when it's air resistance? What's the word for that? Anyone know? What force is that?
Oh, is it drag?
Drag. Very good. There's lift and drag. Okay, so this is really lift and drag. Now, gravity always plays a role here, so we have to really include gravity also. For any of these, it can really be gravity, though, right? All of these involve gravity, except for the tether ball. Because for the tether ball, which way does gravity act? Which way does gravity act, guys? What's the answer? Good. The answer is always down. Which way does gravity always act, guys? Yeah, right? But which way does the centripetal force act now? It doesn't act down, it acts toward the center. So it's like a horizontal force that's changing its direction depending upon where it is. So gravity is not affecting the centripetal force there. An electron in orbit around the nucleus. Not gravity. Not gravity. I mean, listen, the gravitational force exists amongst all objects, and we're going to see that in a minute. But it's not gravity that keeps it in orbit. There's not enough gravitational pull between those two. The masses are so small.
Is it
It's like a magnet. It's like a magnet. You learn about these forces in chemistry or in bio when you're looking at your intermolecular bonds, when you're looking at reactions between things. It's called the electrostatic force. If you don't know, it's not the end of the world if you know the name, but it's the electrostatic force. Similar to the electromagnetic force. Static meaning unchanging. How about a satellite around a planet? What was that? There's only one force that keeps that. Gravity. All right, let's go on to the actual mathematical example now. You know what's really interesting? I went over this example in the other class. And then what happened yesterday at Color Wars? The rope broke. Read this problem. I literally went over this with them yesterday, and for you guys it was today. And what happened in the tug of war? The rope snapped. This is literally the same problem. It's saying what velocity would be needed for there to be enough force in the rope to overcome the 750 newtons available that it can withstand. So the Color War is about to start. I turn to Miss Cusk and go, this is a bad physics problem waiting to happen. She looks at me and she goes, is that rope strong enough? I'm like, absolutely not. Just by looking at it. I see 8 people pulling with about between 50 to 100 pounds of force each. That's 400 or between 200 and 400 pounds of force on each side of the rope. You're talking like 1,000 pounds of force on that rope. And I'm looking at the rope and I'm like, it's going to break. That's really going to break. And what happened? That was so funny. I'm sorry, I mean it wasn't funny, but it was pretty funny. It was pretty funny. Called, I swear to God, I sat there and called, and Mr. Johnson walked over and he goes to me, is that strong enough? And I'm like, I just said to Miss Cuss, that's going to break. And as I'm saying that, it snaps. He's like, good thing I didn't, he was going to run out to one end to like give one group more pull. He's like, good thing I didn't do that. I'm like, yeah, good thing.
I was thinking, shouldn't some of the student government know? Because all of them took the majority of them.
I was surprised. I mean, I have a feeling that somebody ordered something online and didn't physically look at it. But what they should have done is looked at, you need to look at the pound rating. Like, you know the fishing wire that's in there and the dental floss? That has an actual tension strength. The fishing wire says 50 pounds of force. So if you attach more than 50 pounds, what's going to happen? It snaps. There was about between 500 and 1,000 pounds of force on that rope. It snapped, right? Not equal and opposite, but opposite forces providing a lot of tension in the middle of the rope there. Anyhow, this is the same problem, but it's a little bit different because instead of pulling on the rope, this person is like Tarzan, swinging rope to rope. Okay, when will the vine snap? That's what I think about. You ever seen Tarzan the movie, right? When you're a kid? All right, so this is a Project Adventure question. Project Adventure, when I was in middle school, was like you were in a group of 5 and you had to complete an obstacle course, and part of it was like getting between 2 islands, and the ground was lava, you couldn't step on it. So I was thinking about this as an example. Well, if the rope is a certain strength, when will it actually snap, right? So you're given the person has a mass that's fixed. Okay, that's about a 150-pound person. Okay, 150 pounds. The withstanding force that the rope can allow is 750 newtons. Notice my subscript. Why am I going a little further than just FT? Yeah, it's the maximum allowable tension. It's not necessarily what the tension is going to be in the rope. We'll figure out what the tension is in a moment, but that's what it can be up to. Is that clear?
Yeah, so there's one over there, great.
Yeah, so we're going to figure out the force, and if it's more than this, it snaps. If the force is less than this, we're good to go. So this is not the force in this problem. Does everybody see what I'm saying? You're not going to plug this in for F. You're going to figure out F in this problem and see if it goes over that value. This is our limiting factor. So maybe let's do something like this. Let's just put something around it to recognize that it's not actually a given, or it's not going to be used in my equation at least. We know that the length of the rope is 8 meters. I'll put L for now. If I draw a diagram, it makes it obvious what the length actually is. So draw yourself a diagram. Okay, here's your diagram. Here's the person. Here's the attachment at the end of the rope. Here's one island that they're standing on. They're going to swing over to another one. So they're going to end up looking like this. Over here at the end, right? When they're landing on that other island. Now, at a certain point in time, the rope is going to be at maximum tension. Using intuition, what point will that be? Jake? Why? What's your intuition tell you?
I don't know exactly how to explain it, but because at that point, I don't really know how to explain it.
Okay, Ryan, try to help explain it. You're right, though. You're right. It is the middle.
I think it's because gravity, or like it's straight up and down. So the gravity may be stronger at some point.
In the beginning, your gravity pull. Which way does gravity always pull? But in the beginning, gravity's pulling down and the rope is at an angle. So the rope only feels a fraction of gravity, the sine component, sine theta. But at the bottom, which way does gravity pull? And which way does the rope pull? So those are equal and opposite each other, right? So the tension is going to come from all the gravity at the bottom. Why else? Where do you have the maximum kinetic energy? Kinetic energy, not potential. Where do you have the most kinetic? Where? At the bottom. You start with height. When you have height, what do you have? Potential energy. At the bottom, you have all. And then back at the top, you have back to. So at the bottom is when you have the most velocity, right? You have the most velocity at the bottom. So we're trying to figure out what is the maximum speed allowable. So we should look at the bottom because that's where we're going to have the most velocity. When will this rope break? When it has the most velocity. When is that? At the bottom of the path. So let's investigate the scenario at the bottom here. So here's our point. Let's draw a free body diagram on this point. Here we've got tension pulling up. We've got the person's weight pulling down. We've got the circle looking like this. Okay, there's my free body diagram. Why am I drawing the circle? Why is it important that I draw the circle with the free body diagram here? Think about it a moment ago. What did I tell you about the directions of the vectors?
You saw what, FT is positive going in the circle, and FG is negative is going out of the circle.
Do you hear that? You need to say a little louder? A little louder.
FT is positive is going in the circle, and FG is negative is going out of the circle.
That tells you what's positive and negative by the direction it's into the circle or out of the circle. The tension pulls you back into the circle. Where does your weight want to pull you? Your weight wants to pull you down, out of the circle. So we got tension pulling you into the circle, your weight pulling you out of the circle, and that equals ma. But since a is vt squared over r, we use m vt squared over r. Remember, this is, again, sum of the forces centripetally or circular motion equals ma. This is really what the formula is using here. So see the derivation of it. Take a look. It's really sum of the forces equals ma. But what kind of forces are they? They're forces that act centripetally. It might not be a word, by the way. But they act toward the center or away from the center. Okay, they act toward or away. Sum of the forces acting in circular motion equals ma for circular motion. But that is vt squared over r. What is our goal to figure out in this problem? What do we want to figure out? No? Oh, no, yes, sorry. Yes, we want to figure out VT. Absolutely. I was thinking if we were seeing if it snaps or not, if we were given VT. Earlier when we were talking, Ryan, when you were like, yeah, plug it in. If it's more than 750, it snaps. If it's less, it doesn't. This question isn't giving me VT. If I were told that the velocity was a certain value, I could plug in for velocity, for radius, for mass, for weight, and see what Ft is. And if Ft is more than 750, it breaks it. So that was my mistake earlier. We're actually going to use this Ft instead. Because we don't know what the maximum speed is. We're trying to figure out, in this case, what is the value of Vt. That's what we're trying to figure out. So for this problem, there's a problem later, I think, in your notes or in your homework that asks you to find out what Ft is and see if it snaps. So we're given Ft, the maximum allowable tension is 750 newtons. The weight of the person, what is Fg always equal to? Mg. Mg is known. The mass is 60, so let's plug that in. Gravity is 9.81. Why do I not have to put a negative here again? Got to go back. What are we doing? We're looking at free body diagrams. The negative is already taken into account. Okay, the fact that it's pulling down comes into the diagram because we drew the vector arrow acting down. That's why we're not putting another negative here. Don't go back to projectile motion. That's a little misleading, right? And then that equals mass times velocity squared over, what's the radius? It's not 4. It's 8, actually. Let's go through why it's 8. Look at the diagram. Look at the diagram. The length of the rope is 8. Isn't that just the radius of that circle? Okay, look at the diagram at the top. The length of the rope is 8. That's just the radius of a circle if I continue to make the circle. So the radius in this problem is the length of the rope. So we'd have to solve for Vt. What's the number on the left side become?
161.4.
Thank you. I'm going to write it like this. Please take a look. Some of you, I know, expressed to me that you have trouble solving because of the math portions. So let me take a minute to go through that. Here, at this point in time, I see 60 times Vt squared over 8. The way I think about this, well, I could just write this as 60 over 80. And think about it mathematically. What is Vt really over? What is everything over if it's not written? What is it always over? 1. So if I just put this over 1, I get back to this. 60 times this, 8 times 1. Why do I write it like this? Because I visualize this as a fractional coefficient. And when you have a fraction, how do you get rid of a fraction? Multiply by the reciprocal. Multiply by the denominator, divide by the numerator, which is the reciprocal. So multiply by 8 over 60 on both sides. Don't even simplify, guys, honestly. You used to simplify in math, right, all the time. But what does simplifying help me here? It's a decimal answer. So simplifying 60 over 8, that could be 30 over 4, which is 15 over 2, which is really 7.5. Why bother? It's just more steps. Just multiply by the reciprocal, and these are gone. So I do 8 times 161.4 over 60 times 1. Remember, the 161.4 is really over 1. Okay, what do I get for Vt squared before I take the square root? What do I get? Ryan? What is it? And those units are meters squared per second squared. How do I know that? Because I'm going to take the square root. So what does that give me as an answer?
4.64.
Oops. Can I just get a verification? Is that right?
Yeah.
Okay. So, what does this mean? What does this mean? What is this giving me as a number? Explain this answer, the significance. Jake, go.
You can, it would be physically impossible to swing on a rope with a speed greater than
What would happen? Correct. Before you got to any speed greater than this, the rope would break. This is the maximum allowable velocity. The maximum allowable velocity. So again, please, I want you to see something. Everybody, please take a look real quick. I want to point something out. If instead of giving you the maximum allowable tension, look up, please, look up, come on. Instead of giving you the maximum allowable tension, if you were given the actual velocity, you could calculate the tension and see if it exceeds the maximum allowable tension. Again, if this was left alone as Ft, it was unknown, you could be given Vt instead, and then you would be given all of these, and you could calculate the tension felt and see if it exceeds 750, if it will snap or if it won't snap. Do you see how this problem could vary by changing one thing? By giving you velocity, you could figure out if it snaps instead of telling you what would cause it to snap and figuring out that velocity instead. What's that?
So it's not wrong to multiply by 8, because I just did 60 VT over 8 and then multiply by 8.
Again, multiply by 8, divide by 60, same thing. Yep.
But then, if you did that, you still need FT though.
No, you'd be solving for Ft is what I'm saying,
Right.
Ernest. You'd be given Vt. You'd have to be given the velocity.
But then how can you compare, like,
Whatever answer you get, let's say I get an answer of 300. Is 300 more than 750?
I'm saying if they give you 750, don't
No.
so you already have.
750 is the maximum allowable tension in the rope. It's not necessarily what the rope is going to feel. If the problem says the maximum allowable tension is 750, determine if the rope will snap. That means you need to figure out the tension and see if it exceeds 750.
I thought 750 was already max.
It could be given. No, it is the maximum. What I'm saying is if they gave you the velocity and the question were then posed as, will it snap? That's asking, figure out the tension. Is the tension more than the maximum allowable? Okay, so this would be the unknown in that case. Let's finish up. What's the examine schedule so I know?
We end like a minute for
10, 11.
10, 11. So we got about 2 minutes. All right. So let's talk about gravity real quick. Gravity we talked about already in the introduction that it exists amongst all masses. The formula here is mass 1 times mass 2 over r squared times this capital G. This capital G is a constant. It is a constant for any two objects anywhere in the universe. It will never change. It is a universal constant. What is the G that we know? That's the constant where? On Earth. On the moon it's 1.6. On Jupiter it's like 26 point or 25.2, whatever it is. This is capital G. This is not the gravitational constant on Earth. This is what's called a universal gravitational constant. It is a value that works in this formula. It is a value that was experimentally determined. The way it was determined by using an experiment, by knowing the masses of two objects, how far apart they were, by being able to measure the pole between them, this was actually calculated. It's not really how it was done, but that's how the value comes about. It's an experimental value.
So you say like gravitational force kind of acts like down and up and away.
So gravitational force on Earth, we say acts down, right? But if you're in space and you're here and a satellite is here, gravity pulls you toward each other. If you're not in contact, right now, that calculator is pulling me toward it. Matei, you're pulling me toward you. This paper is pulling me toward it. Every object pulls you toward it. It's just that the Earth is so much stronger in its gravity that you don't feel the other objects pulling you. But if you're in space and there's nothing near you physically, then the object closest, even if it's like a small object, would pull you. I mean, nothing big, right? If you're not near the sun, if you're outside of the real field of the Earth, you're so far away. Look at R. R is the distance between the two objects. It's all right. It's all right. It's all right. So it's the distance from the center to the center of the objects. So if I am so far away from the Earth, my R value becomes so big. Please, you need to listen, guys. Come on. Your R value, look at the board, becomes so big. And this is indirectly related. So if R becomes really big, the force of gravity becomes really small. If you're closer to something, you have more of an attraction to it. If you're further from it, you have less of an attraction of gravity. Gravity is only an attractive force. It is not a repulsive force. It can't push two things apart. It can only pull them together. Gravity is based directly on the masses of the two objects at hand and this constant. It is based indirectly with the square of the distance between their centers. Okay? This idea revolutionized physics. Newton's law of gravity allowed so many other advancements to take place. We're going to finish this tomorrow with 9.4 together. And 9.4 comes about because of this. 9.4 is Kepler's laws. They came about because of Newton. Newton's laws started everything. Okay, so tomorrow we'll do an example. We'll take a look at examples number 4 and 5 tomorrow to start. So we've got 2 dump trucks in this example. The reason I use this example is because I want to emphasize the fact that even things as big as dump trucks don't really exert much gravitational pull. Look at the value of the force it's given. The gravitational force is 4 times 10 to the negative 5. So 0.000004 newtons. We're talking about a very, very small amount of force, to the point where that is not even close to the amount of force that friction can withstand with tires. So if you think about it, even if the trucks wanted to pull toward each other because they're so massive, the friction between the tires and the road would easily be greater than the force that they're feeling that's pulling them together. Think about your magnitudes of friction. We've talked about frictional forces on the scale of like 100 newtons, 50 newtons. This value is, again, 0.00004 newtons. So although these two objects are feeling a pull together because of gravity, friction between the tires and the road is like, are you kidding me? I'm not going to move. It's like me trying to push the podium with one finger by barely pushing. That would be the equivalent. Okay, the trucks are feeling the smallest amount of pull toward each other. The earth is pulling it down with a huge amount of gravity. Everything around it is so much greater than the gravitational pull between the two trucks that they're not actually pulling toward one another. Is that clear what I'm saying? But really, like mathematically, all things have gravitational pull toward all other things. Because if you have mass, clearly with the formula we saw on the previous slide, you have to have a gravitational field or pull about your body. So we're given the gravitational force here. We're told that the objects, the dump trucks, are 5 meters apart. So maybe there's like one lane in between them. From center to center, because we're not going to take a look at it's not like remember yesterday we talked about R being the distance from center to center. For planets, we have to consider the fact that the planet's center is not really near its surface. Whereas the trucks, the actual dimensions of the trucks are so small that 5 meters is reasonable. For planets, we have to consider that if I had, let's say, we didn't go over this, right? I did with the other class. We have the Earth and we have the Moon. The Earth's center is here, the Moon's center is here. If we think about the distance between the Earth and the Moon, it might be tempting to say, okay, the distance between the Earth and the Moon is simply this segment right here. But why is that not really correct? What are we talking about really?
Maybe that's not like the center to center.
Yeah, it's not center to center. So what do we have to include?
Would you start from the bottom?
Start from where?
That's the bottom.
Not the bottom. We've got center to center. From center to center. Yeah, start from the center of the Earth and go all the way to the other center of the Moon. So technically speaking, for a problem where you have planetary motion, because one of your homework problems has this and one of your problem sets also. For a problem where there are two celestial bodies that have a huge radius, you have to include their radii. Think about that length that's in blue in front of you here, okay? That is equal to the sum of the Earth's radius, which is right there, whatever this gap is, and then the Moon's radius. It's technically 3 segments. The radius, the gap between the planets, the next radius gives you that entire length. From geometry, segment addition postulate simply tells you if you got 3 segments that are collinear and you want to find out the overall length, just add them together. So we have the radius of the Earth, the gap, we're calling that D, the gap between the surfaces, and then RM. Okay, if you can't see that, I'll zoom in a little bit. Okay, RM, the radius of the actual Moon itself. So if I were to draw this with 3 segments, I'm thinking about the radius of the Earth, the gap, the radius of the Moon. I drew it below it, but I would obviously draw it on the diagram. Okay, I drew it below so you didn't have to see the color get all mixed up. But you've got those three segments you would use. And where would that go? Well, in the formula, we're going to use this formula in a minute for the dump trucks. But in this formula, that value would go in the denominator for r. So the denominator is r squared, right? In this formula we just saw? Well, r is the distance from center to center. So it would be this. Okay, so put a little side note, please, for this problem. Don't write it maybe in the same spot, but put a side note and just say for planets and stars and moons, we have to consider their radii because they are so large that they do affect the answer. Whereas a dump truck, we're just telling you 5 meters center to center. The dimension of the dump truck is so small already, it doesn't affect it, okay? So that would be something for planets or stars or moons. We have to consider the gap between the planets or the planet and the moon or the planet and the star, and then the radius of each of those masses also added on. All right, let's jump back into this problem now. So that's just a side note again. It's not actually part of this problem. And in this problem, we're told again that the center to center distance is 5 meters. They're 5 meters apart, center to center. We're told that the gravitational force between the trucks is 4 times 10 to the negative 5 newtons. We know that they have equal mass. Can somebody give me a statement from that, please, that I can write that would be useful? Useful?
M1 is equal to M2.
So if I could just call them both what then?
M.
Good. Remember, when the masses are the same, why do I want to call them just M? Explain to me why again. Do I not want to call them M1 and M2? If they're the same, you could use the same value, so why am I just using M instead of M1 and M2?
Well, you can just use M because they're the same value. It doesn't really matter.
But why does it help me, I'm saying? Like, look at this problem, look at this formula and stuff.
It's going to make it less confusing.
Yeah, it makes it less confusing because what?
You only have one unknown to find.
You only have one variable unknown now. Again, what were you looking for in this problem? You're trying to figure out the mass of the trucks. Well, if they're the same, just call them M. It makes it easier because look, this formula, get rid of the subscripts. Get rid of the 1 and 2 subscripts. And what does this formula become as a result? Get rid of the 1 and 2 subscripts. What does it become?
G2M.
Careful. That would be M plus M, would be 2M.
Oh, M squared.
There you go. Be careful, please, because that is something that it's not just you that said. The other class had the same thing. Right off the bat, somebody said 2M. Be careful. It's M times M, M squared. Now, you know everything except for M. Big G is a constant. 667, 10 to the negative 11. It's on your formula sheet. It's on the previous slide. Okay, it's a constant. You never have to memorize it. R is the distance from center to center. That's 5. FG was given as 4 times 10 to the negative 5 newtons. So literally at this point, all you have to do is plug in. Okay, if you want to solve for M algebraically, you could solve for M algebraically or just plug in numbers. I'll do it both ways. I'll solve algebraically up here, and down here I'll plug in numbers. So if I just plug in numbers, it looks like this. And you got to be careful with your scientific notation here. It comes up a lot in this section. Why does it come up a lot? What are we looking at? Small and big numbers. The mass of the Earth is going to be huge. The radius of the Earth, huge. Well, suddenly we've got G, really small. So because of that, we have to worry about the fact that we always have scientific notation. So to get rid of the 5 squared, I would multiply both sides by 25 and then divide by 667, 10 to the negative 11. That'll get you M squared by itself. Again, multiply by 5 squared, divide by 667, 10 to the negative 11.
Yeah, so if you run strictly, wouldn't it be
Go ahead.
times R squared over G,
Very good.
both sides,
Equals
equals
M.
M squared,
Yeah.
M squared.
And then if I want to get M by itself, how do I get rid of the square?
Oh, square root.
So this is the algebraic solution. That's what Ernest was just asking. If you want to solve it in terms of variables, you would take the R squared, multiply it up. Here, take the R squared, multiply it up, divide by G. That leaves you with M squared. And then to get M, just take the square root of that expression. Either way, I'm going to give you the answer because I do want to press on. The answer turns out to be 3,872 kilograms. If you didn't get that, maybe you got a much larger number, make sure you remember to square root your answer, because you might have solved for m squared and you got to square root it in the end. Again, multiply by 5 squared, divide by 6, 6, 7, 10 to the negative 11, get an answer, square root it. So this is about 10,000 pounds, which is reasonable. A car is like between 1,000 and 2,000 pounds, and a dump truck is at least 5 cars. They're much larger and they're made of mainly like steel, and then they carry things, right? So a dump truck usually has a mass supply in the back. About 10,000 pounds or so. So I need you to be ready to answer questions on this topic that also relate to planets and stars and moons and stuff. So when you practice this, make sure to see this little note that we wrote up here at the top right. Is that clear what I'm saying right now? Make sure that you look at this little note when you're looking at maybe your homework and your problem sets. Okay, this would be very useful to look at this part. Okay, that other note, because you're going to need to consider the radius of those planets.
When we calculate, can you just do like 4 times 10 to the negative fifth?
Yeah, you press 4, then
Right.
press second,
Just making sure there's-
press second, and then there's a capital EE somewhere. It's in like yellow or something. It's one of your second commands. It's like at the comma. Look for the comma or apostrophe. Look for capital EE as a command above one of the actual keys. It's like above, you see it? It'll bring up a capital E on your screen. Then just type in -5. So 4, then press the EE key, then press -5 and hit enter. You see that's the number? That's how scientific notation is used in the
I
calculator.
don't know.
Oh, you got it.
Yes, but I got it. It came up as 3 times 2.
It means somewhere you made a mistake with your exponents. Go back and look through. Okay? It just means you made a mistake with exponents somewhere. Because think about it. To be off by a factor of 3, or a factor of 1,000, means that 10 to the 3 was off somewhere. So there's a mistake with exponents somewhere along the way.
Okay.
Okay? I do want to press on though, guys. So if you're having trouble with scientific notation, don't let it go though. Please, individually, come see me and I'm happy to go over it with anybody. Free period after school, just come by to ask though. I'm not going to stop during class to go to everybody's calculator now, right? But if you need help on that, please ask me. Don't just let it go. In the last problem, we take a look at a scenario that I always ask as a question on every single test. What happens as something varies? That's the question I always ask, right? If the mass doubles and the velocity triples, what happens to the kinetic energy? Like that was one of your midterm questions, right? Where they both tripled or something. Here, same idea. You want to answer? You have a question? Yeah. Tell us what we would do at least, Jake. First, do you remember the process?
Yeah, so would it be smart to like write out the formula?
Yep. It would be very smart to start with the formula. You could always plug in numbers, but it takes longer to plug in numbers. That's why I do it this way. Jake, what's changing in this problem, Jake?
Well, it said if the distance between the two objects doubles.
All right.
There's a gravity, so since r itself is squared, if you double that, then the denominator would just make it bigger, so the force is automatically gonna decrease.
By what factor, Jake? Decrease by factor of what? What number is going to appear in the denominator?
1/4.
Yeah, you could say decrease by a factor of 4, or it's 1/4 of what it was. Okay, but do we see? Take a look. This kind of a problem says if the distance from center to center, which is called r, doubles. Remember, when you have a product to a power, you have to raise each factor to that power. So this becomes, oops. Did my iPad just freeze? Oh, no, it's the pencil. This becomes GM1 M2 over 4R squared. That's the key here. When you double the distance between the centers, you quadruple the effect of decrease. Why is it an effect of decrease? How are FG and R related? How are they related? And I've heard you've been doing this in your math class. Indirect and direct variation, joint variation. This is joint variation. The force of gravity varies jointly with the masses of the objects, and it varies indirectly with the square of the distance between them. What's your constant of variation in this formula? G. G is the universal gravitational constant. G is your constant of variation. So in your math class, when you have these examples that might have just numbers, this is literally where it comes from. It varies jointly with the masses, and indirectly or inversely with the square of the distances. And the constant of variation is g. Okay, keep that in mind. That's how these are related. Jake, what's up?
If this was triple, then it would be decreased by a factor of 9.
9. Again, triple would be 9 because you put a 3r, which becomes 9r squared. Okay, yes?
Or do you give a factor, if you say, so you can say 4 or 1/4?
You could say it is cut in 4. You could say it is 1/4 of what it was. You could
Okay.
say it decreases by a factor of 4.
Okay,
But if you said it decreases by a factor of 1/4, it's kind of like a double negative.
okay.
Or a double negative becomes positive. So by saying decrease, you say decrease by a factor of 1/4. That would mean you divide it by 1/4, which really increases it by 4.
Got it.
So you wouldn't want to say decrease in 1/4, decrease in 4, you're saying. Follow-up question for you. Because on the midterm, some people struggle with this one. And this was a question about power. And it was like, you lift 3 times as much mass as your friend, but it takes you twice as long. It was 3w over 2t, which became 3 halves. Well, let's take a look at this now here. What if the mass is tripled? What if the masses in this problem tripled? Well, there'd be a 3 here now, and a 3 here, which inherently would put a 9 out in front. Do people see what I'm saying right now? If the masses both had tripled, while at the same time the distance doubled, triple mass looks like that. 3 by 3 is really, and no, because multiplication is commutative, I can take the 9 and put it where? Right out in front. So do you see the 9 over 4 right now? You would say it changes by a factor of, what is it? 9/4. Okay? If it was 7 over 2, changes by a factor of 7 halves, or 3.5. 9/4 is what, 2.25? So changes by a factor of 2.25. If the case were that the masses were also tripled. Please write yourself a note. This is not the right answer to this problem. I'm saying, what if now the mass is also tripled? All right, we got to stop it there because we do have the other lesson to get to.